Good morning, students. Today we are going to the third class of final BSc paper 6 mathematics, that is linear algebra. For the first unit, that is vector spaces 1, we are going to third class. In the previous class, we have learned two theorems. Those are intersection of two subspaces is a subspace. The second one is intersection of arbitrary family of subspaces is again a subspace. Now today we are going to learn another theorem, that is theorem 4, that is on the union of subspaces. The statement, theorem 4 is the statement, go to the screen, union of two subspaces of vector space V over the field F is subspace of V if and only if one is contained in another. There is a direct statement is there, or if W1 and W2 are two subspaces of vector space V over the field F, then W1 union W2 is subspace of V of F if and only if either W1 is contained in W2 or W2 is contained in W1. If and only if IFF is there, that means necessary and sufficient condition, we have to prove this theorem. The left hand side part is W1 union W2 is subspace of V, and the right hand side part is either W1 is contained in W2 or W2 is contained in W1. The common portion is W1 and W2 are two subspaces of vector space V over the field F. This is the common portion to prove the necessary and sufficient conditions. So the theorem is in three parts, that is in 3 pages. The first page of this theorem proof is, first of all, we want to take the W1 and W2 are two subspaces. That is, suppose W1 and W2 are two subspaces of vector space V over the field F. Necessary condition. Suppose we have to take, I am taking right to left. That is, necessary condition is either W1 is contained in W2 or W2 is contained in W1. Suppose I am taking that either W1 is contained in W2 or W2 is contained in W1. We want to prove this one. This is W1 union W2 is subspace of V of F. We prove that W1 union W2 is subspace of V of F. To prove this one, we know that W1 and W2 are separately the subspaces of vector space Vf. So this vector space has identity vector 0 bar, that is 0 bar belongs to W1 and also 0 bar belongs to W2. 0 bar belongs to both W1 and W2, means 0 bar is also in the union W1 union W2. That means W1 union W2 is not an empty set, that is non-empty. And also clearly W1 union W2 is in V, because W1 in V, W2 in V. So W1 union W2 is also in V. Okay, right. Now we are taking the condition W1 is contained in W2. In both cases, there are two conditions are there here. What are they? W1 is contained in W2 or W2 is contained in W1. In both cases, we have to prove W1 union W2 is subspace of V. So I am taking the first case. If W1 is contained in W2, if W1 is contained in W2, that means this is the diagram. The red one is W1, the blue one is W2. If you go to the Venn diagram, red one is the W1 and blue one is the W2. W1 is in W2. This is the symbol. W1 is contained in W2 means W1 is the set in W2. Then what happened if we union these two sets, W1 union W2? Then it gives W2 only. W1, W2. If we add these two sets, then what happens? W2 is the set. The union of W1 union W2 gives W2. Okay, we know that W2 is a subspace. W1 means, W2 is a subspace. W2 means W1 union W2. That means W1 union W2 is subspace of V. Right. In this condition, W1 contained in W2, we prove that W1 union W2 is subspace of V. Now in the other condition, if W2 is contained in W1, what I have told, W1 is red, W2 is blue. Here W2 is contained in W1. W2 is contained in W1. That means if W1 union W2, what happens? The total W1. Yes, W1 is the big set. That's why W1. We know that W1 individually is a subspace. Here W1 means W1 union W2 is subspace of V. In the first case, W1 is contained in W2. We prove that W1 union W2 is subspace of V. In the second case, if W2 is contained in W1, we prove W1 union W2 is subspace of V. In both cases, we proved that W1 union W2 is subspace of V. That means necessary condition is over. Then we go to sufficient condition. What is that? In that sufficient condition, we are taking that suppose W1 union W2 is subspace of V. W1 union W2 is subspace of vector space V over the field F. We prove that here either W1 is contained in W2 or W2 is contained in W1. We want to prove like this. But in contrary way, that means in the wrong way, I am assuming that W is not contained in W2 and also W2 is not contained in W1. Means W1 is not in W2 and W2 is not in W1, not contained in W1. That means all the elements of W1 are not in W2. This is the meaning of this W1 is not contained in W2. W1 is not contained in W2 means all the elements of W1 are not in W2. That means some extra elements are in W2. I am taking that here W1 is not containing in W2 means W1 has an element that is not in W2. I am taking that there exists an element alpha in W1 such that alpha is not belongs to W2. Similarly, for W2 is not containing W1, there is an element in W2 and not containing W1. That means there exists beta belongs to W2 such that beta does not belongs to W1. For the both conditions, I am taking that alpha is W1, alpha is not in W2, beta is in W2 and beta is not in W1. I am taking these two as 1 and 2. Right. Now alpha is in W1, beta is in W2 means alpha and beta are both are in W1 union W2. Alpha comma beta are in W1 union W2. But W1 union W2 is a what? W1 union W2 is a subspace of V. Means subspace means vector space means closure law exists. That means alpha comma beta belongs to W1 union W2 and W1 union W2 is subspace. By closure law, alpha plus beta belongs to W1 union W2. Alpha plus beta belongs to W1 union W2 means alpha plus beta is in W1 or alpha plus beta is in W2. Sorry, it is wrongly written that I am correcting it. Just I have corrected it. Alpha plus beta belongs to W1 union W2 means alpha plus beta belongs to W1 or alpha plus beta belongs to W2. In both cases, we have to get the contradiction because we are going in the contrary way. In that contrary way, we got two ways. We have to prove these two ways are wrong. First, I am taking that this way, that is alpha plus beta belongs to W1. We know that alpha belongs to W1. We have that alpha belongs to, students kindly follow the cursor. Alpha belongs to W1. Cursor is rolling there. Alpha belongs to W1. Alpha plus beta belongs to W1. And W1 is a subspace of V. That means by known W1 is subspace. That means alpha plus beta minus alpha belongs to W1. Plus alpha minus alpha then cancels, then what happens? Beta remains. Beta belongs to W1. But beta does not belongs to W1. From 2, beta does not belongs to W1. But we got beta belongs to W1. That means this is contradiction to 2. Which is contradiction to 2. What is 2? Beta does not belongs to W1. But we got beta belongs to W1, which is contradiction. That means this way is wrong. There is another way is there. That is, if alpha plus beta belongs to W2. Now we are going to that way if alpha plus beta belongs to W2. We know that beta belongs to W2. Beta belongs to W2. Are you watching the cursor? Beta belongs to W2. Now I am taking that beta belongs to W2 and alpha plus beta belongs to W2 and W2 is a subspace of V. By using subspace condition, alpha plus beta minus beta belongs to W2. This is subgroup condition. Plus beta minus beta will cancel, then alpha remains. That means alpha belongs to W2, which is contradiction to 1. What is 1? Here is 1. What is 1? Alpha does not belongs to W2. But what we got here? Alpha belongs to W2, which is contradiction. What is that? In this way also we got contradiction. That means we got contradiction in both cases. That means our assumption W1 is not contained in W2 and W2 is not contained in W1 is wrong. Therefore, either W1 is contained in W2 or W2 is contained in W1 is right. Hence, the theorem was proved that union of two subspaces of vector space V over the field F is subspace of V if and only if one is contained in another. Okay, students? Now we go to the third one. That is theorem 5. What is that? If W1 and W2 are two subspaces of vector space V over the field F, then W1 plus W2 is subspace of V of F. Second one, W1 is contained in W1 plus W2 and W2 is contained in W1 plus W2. If we take W1 and W2 are two subspaces of vector space V of F, then we have to prove these two bits. So for that, I am taking that. Suppose W1 and W2 are two subspaces of vector space V over the field F, that is V of F. What is that? What we have to prove in the first bit? W1 plus W2 is subspace of V of F. Now we prove that W1 plus W2, that the elements in the W1 plus W2 set is like that. Alpha 1 plus alpha 2. Alpha 1 is in W1, alpha 2 is in W2. Okay? Alpha 1 belongs to W1, alpha 2 belongs to W2 is a subspace of V. We have to prove W1 plus W2 is subspace. For that, first of all, we want to prove that this set is non-empty. We know that separately, W1 and W2 are subspaces. That means 0 bar belongs to W1, 0 bar belongs to W2. 0 bar plus 0 bar. First 0 bar belongs to W1 and the second 0 bar belongs to W2. That means 0 bar plus 0 bar belongs to W1 plus W2. Means 0 bar plus 0 bar means 0 bar belongs to W1 plus W2. That means W1 plus W2 has an element. That means W1 plus W2 is not empty. And also clearly W1 plus W2 is contained in V. Now I am taking that alpha comma beta belongs to W1 plus W2 and A comma B are scalars in F. If alpha belongs to W1 plus W2, then all the elements of W1 plus W2 are looking like, what is that? Alpha comma beta belongs to W1 plus W2 means alpha is in the form of, in the W1 plus W2 set, what are the elements are there? How they are in W1 plus W2? Alpha 1 plus alpha 2. Alpha 1 belongs to first beta 1 and alpha 2 belongs to W2. Alpha 1 belongs to W1, alpha 2 belongs to W2. In that case also, alpha is in W1 plus W2 means alpha is in the form of alpha 1 plus alpha 2. That alpha 1 belongs to W1, alpha 2 belongs to W2. Similarly, beta is also in W1 plus W2. That means beta is in the form of beta 1 plus beta 2. Beta 1 is in W1, beta 2 is in W2. That means alpha 1, beta 1, the first elements are in W1. Second elements, alpha 2 and beta 2 are in W2. But W1 and W2 are two subspaces. If W1 is subspace, then the theorem, by theorem 1, A alpha 1 plus B beta 1 belongs to W1. Because W1 is a subspace and alpha 1 beta 1 belongs to W1 and A comma B are scalars in F. That means A alpha 1 plus B beta 1 belongs to W1. Let it be 1. And also alpha 2 beta 2. Alpha 2 beta 2 are belongs to W2 and A comma B are in F. And also W2 is subspace of V. That means again by theorem 1, A alpha 2 plus B beta 2 belongs to W2. Let it be 2. From 1 and 2, if we observe that A alpha 1 plus B beta 1 belongs to W1, A alpha 2 plus B beta 2 belongs to W2. We can note it and we can go to the next step, that is next page. What is that? Now I am preparing A alpha plus B beta. I am preparing A alpha plus B beta because what we have taken, alpha comma beta belongs to W1 plus W2. We want to show W1 plus W2 is subspace. That means we have to prove A alpha plus B beta belongs to W1 plus W2. For that I am taking A alpha plus B beta. A alpha, what is alpha? What is alpha? Alpha 1 plus alpha 2. What is beta? Beta 1 plus beta 2. We substitute here. A into alpha. Alpha is alpha 1 plus alpha 2 plus B into beta plus B into beta 1 plus beta 2. Then what happens? A alpha 1 plus A alpha 2. Written plus is written B beta 1 plus B beta 2. Scalar is multiplied. A alpha 1 plus B beta 1. Ones are arranged in a single place. Plus A alpha 2 plus B beta 2. A alpha 1 plus beta 1 belongs to, kindly go to the next previous step. A alpha 1 plus B beta 1 belongs to W1. A alpha 1 plus B beta 1 belongs to W1 plus A alpha 2 plus B beta 2 belongs to W2. If you go to previous step, that is second step, A alpha 2 plus B beta 2 belongs to W2. A alpha 2 plus B beta 2 belongs to W2. A alpha plus B beta 1 belongs to W1 plus S is A alpha 2 plus B beta 2 belongs to W2. That means A alpha plus B beta belongs to W1 plus W2. What is that? Alpha beta taken in W1 plus W2. A comma B are scalars in F. Then what happens? A alpha plus B beta belongs to W1 plus W2. Means W1 plus W2 is subspace of V of F. The first bit is over. Now we prove the second bit. What is that? W1 is contained in W1 plus W2. Okay, right? Alpha 1 belongs to W1. We know it. 0 bar belongs to W2. Because W2 is a subspace, it has identity element. Now alpha 1 plus 0 bar. Alpha 1 belongs to W1. 0 bar belongs to W2. That means alpha 1 plus 0 bar belongs to W1 plus W2. Then what happens? Alpha 1 plus 0 bar is alpha 1 because 0 bar is the identity. That means alpha 1 comes out. That is alpha 1 belongs to W1 plus W2. Alpha 1 is taken in W1. Alpha 1 is in W1 plus W2. That means W1 is contained in W1 plus W2. What is that? W1 is contained in W1 plus W2. How we can say that? Alpha 1 is W1, but alpha 1 is also in W1 plus W2. That means all the elements of W1 are in W1 plus W2 means W1 is contained in W1 plus W2. Similarly, we prove that W2 is contained in W1 plus W2. You have to, all of you try in this in your home to prove this step. Similarly, like this. Hence, we say that either that means W1 is contained in W1 plus W2 and W2 is contained in W1 plus W2. The second bit is also proven. So we have learned here the theorems. So students, I am posting this in your group, in WhatsApp group, in PDF file format. So kindly write down the notes and I will check in the next class. Okay, right. Thank you.